We are Team 1, Everything's Fine. Our group members are Catalina Nguyen, Cole Messina, Paul Kim, and Robert Marcel. We will be discussing the design process of creating our machine for the Mission to Mars ME 2110 competition.
One objective of the competition is clearing radioactive elements. Each radioactive element in the home zone is -6 points. Another objective is landing spacecraft safely. Each spacecraft landed in a safe zone is worth 15 points, and each spacecraft landed in an unsafe zone is worth -20 points. Each astronaut or rover is worth 28 points for full retrieval and 14 points for partial. The rock samples are each 18 points for full and 9 points for a partial retrieval. Placing a flag is worth 60 points. The main objective of the machine is to be able to consistently score as many points as possible in order to outscore other teams and advance to the next round of the competition.
This function tree displays all of the functions that the machine must be able to perform in order to complete the competition objectives. The function tree shows that many subfunctions of the machine involve extending out towards the center of the track. While it seems that the machine has many functions to accomplish, an efficient design can combine solutions to related functions. In this morphological chart, various solutions to each function of the machine are listed. Many similar subfunctions have the same possible solutions. For example, multiple functions related to extension have drawer slides as a possible solution. The solutions in the morphological chart were used to develop 4 design alternatives for the machine. Each design alternative only addresses 4 of the 5 objectives for the competition. This was done to ensure that the design focused on consistently scoring points. The machine would score more points on average if it could achieve 4 objectives with consistency rather than attempt 5 objectives without consistency.
The first design alternative completes the spacecraft, flag, astronaut rover, and rock collection tasks. A platform with the spacecraft, flag, and astronaut rover subsystems slides towards the center of the track. A switch on the platform senses safe zones as the mountain ridge rotates. And once a safe zone is detected, the spacecrafts are released into the mountain ridge by a solenoid. A folding arm is deployed by a mousetrap and places the flag over the center of the mountain ridge, while another arm connected to the flag arm lands on top of the mountain ridge, knocking astronauts and rovers into the home zone. Rock collection arms fall forward and land around the rocks. The arms are connected to horizontal drawer slides on the base that extend backwards as they pull the rocks into the starting zone. Design 2 completes the same tasks as Design 1. The spacecraft, flag, and astronaut rover tasks are accomplished in the same manner as Design 1, but a different method is used for the rock collection. Rock collection arms are connected to a second angled set of drawer slides that extend into the track, allowing the arms to fall past the rocks onto the track. Once the rock collection arms land past the rocks, the drawer slides are pulled back in, bringing the arms and rocks into the starting zone.
In Design 3, the spacecraft, flag, and astronaut rover subsystems sit on a platform that slides out on drawer slides to the mountain ridge. The flag arm and astronaut rover arm are deployed by a mousetrap and extend over the mountain ridge, suspending the flag over the center and knocking over astronauts and rovers. Instead of sensing when a safe zone passes by, the machine will release the spacecraft after a preset amount of time has passed. 3 switches at the back of the machine correspond to different time constants, with the appropriate switch being pressed prior to the machine's operation. Based on the initial orientation of the mountain ridge, the team would select the switch that will result in the correct timing to release the spacecraft in a safe zone. Design 4 completes the spacecraft, flag, and astronaut rover tasks with the same methods as Designs 1 and 2. In addition to completing these tasks, Design 4 clears radioactive elements. Pneumatic cylinders knock over hinged arms, which land on the radioactive elements, pushing them out of the home zone. The 4 designs were compared in an evaluation matrix, which determined that Design 1 was the best design. Design 1 scored the highest in the evaluation matrix due to its ability to consistently score the most points. Because the release mechanism for the spacecraft in Design 1 relies on a continuously running sensing method, the spacecraft can be landed on a second or third try if something goes wrong the first time a safe zone comes around. The rock collection for Design 1 is also more consistent because the horizontal drawer slides don't have to be pulled against gravity as the rocks are pulling in. As a result of these advantages, Design 1 was chosen as the final design.
Here's our final design for the competition. As you can see, there is an exterior frame, making the boxing process easier. In the center, our design has cascaded drawer slides and a main center extension. The spacecraft are resting in a PVC pipe and the rock collection arms are folded back on top. On the base, the MyRio and other motors are mounted. The spacecraft are held back by an extended solenoid. The rock collection arms are mounted with a hinge to drawer slides mounted on the base. At the instant the track is started, the pneumatics extend forward. A half-second later, the large solenoid shown retracts, allowing the entire center assembly to slide forward and extend. The rock collection arms fall past the rocks, and the mouse traps open the side arms. A spool on the DC motor, which is mounted on the base, begins to spin, pulling the rock arms and the rocks back into the starting zone. The center assembly is extended so the switch contacts the safe or unsafe beacons on the rotating mountain ridge. When the switch is pressed twice within 1 second, the smaller solenoid retracts, releasing the spacecraft into the safe zone. The other DC motor pulls a pin out of a mousetrap, deploying the flag arm and angled arm. The angled arm is on a free pivot, allowing it to adjust to various track heights or differences. The angled arm knocks the astronauts and rovers into our home zone, and the flag arm holds the flag above the cylindrical cavity of the mountain ridge.
In our qualifying competition, we scored 72, 100, and 100 points in the first, second, and third rounds respectively by accomplishing the flag, spacecraft, and astronaut rover tasks. We were seated 9th place. Before the final competition, we improved the flag and astronaut rover arm to increase the consistency and added the rock collection subsystem. During our testing, all the subsystems were very consistent, and we successfully planted the flag, saved astronauts and rovers, landed spacecraft safely, and retrieved rock samples, as can be seen. We nominally scored between 110 and 130 points on an average round during testing.
Similar to our testing, we successfully accomplished 4 tasks in the first round of the final competition, as well as saving an extra half astronaut, giving us 141 points. This put us in first place for our first round and guaranteed us an appearance in the third round. Our driver board decided it had had enough. For the second round, none of our digital outputs worked, resulting in a disqualification and 4th place for the round. After hurriedly replacing our driver board, our machine would only work on random occasions, and we had no idea if it would trigger or move at all. For round 3, it did end up triggering, but during the replacement of the driver board, a wire got caught on the pneumatic actuators. This prevented the machine from reaching its full extension, and none of the competition tasks were completed. This resulted in a score of -60 and 4th place in the third round. Disregarding the driver board failure, our machine could benefit from better cable management and more weight on the rock collection subsystem. This could help prevent a couple of the problems that contributed to the machine's failure in round 3. Thanks for watching, and remember, everything's fine.